All right. Thanks for the opportunity to talk today. Again, this is going to continue on the vessel avoidance topic here, but on Lake Erie, and then hopefully also touch on some other information that we gained from the survey and how that might inform the next steps for hydroacoustic survey design. As has been mentioned, this is a large collaborative effort. There's been a host of different agencies and institutions that have contributed to this. Specifically on Lake Erie, we've worked very closely with Ohio DNR, Ontario Ministry of Natural Resources, Cornell University, SUNY Brockport, Brooklyn College, as well as Michigan Technological University. I won't belabor this too much, but it is important. Fisheries acoustics is a unique way to sample fish, and it has a lot of benefits. Gives us a unique perspective of fish distributions and abundance through the water column, and we can collect that information over large spatial scales. This is a cross-lake echogram from Lake Erie, and it's just showing the distribution of fish and their association with a very dynamic thermocline, something that would be hard to track with trawls alone. As has already been mentioned as well, there's a legitimate concern about the noise produced by research vessels and the potential for them to move fish out of the path of the vessel and therefore bias our survey estimates. So again, we've worked with, or we're using sail drone or uncrewed surface vessel to test the potential for this bias in our surveys. We've heard and seen a lot about the sail drone so far, but just want to put some numbers to the scale. It is quite large, so it's 23 feet long, 15 feet high off the water, and extends 6 feet down into underneath the water. It is outfitted with a range of different sensors, so we're collecting information above and below the water, along with the hydroacoustic data that we're collecting. Just some visuals of the sail drone here. This is during the deployment on Lake Erie out of Erie, Pennsylvania. So again, just to give you kind of an idea of the size here, and again, you can see some of the sensors, the solar panels and GPS units and whatnot there. All right, so once this is out on the lake, just how do we interact with it? The sail drone's tasked with daily missions, so we send it waypoints, and then once those are transferred to the drone, it achieves those waypoints automatically by adjusting its sail and rudder position based on the ambient conditions that it's experiencing. So we can adjust its positioning and routes in near real time through coordination with the proprietor. On Lake Erie, the USV was at large for 58 days, from August 1st to September 27th, and it collected nearly 3,600 kilometers of hydroacoustic data. Our primary goal there was to interact with vessels similar to the other lakes. And we did that with 4 different vessels, 2 Ohio DNR vessels in the Western and Central Basin, 1 USGS vessel in the 2 parts of the Central Basin, and an Ontario vessel in the Eastern Basin. So these are the 4 general areas that we were able to interact with those vessels. This is another description of how we interacted with them. We undertook these overtake maneuvers, so we would set the sail drone on a single course, and then that would proceed, and the vessels would hop on the course, approach the sail drone, and move off because the sail drone moved at much slower speed. So we kind of had to adapt a traditional method here. This particular night, we were able to collect 6 overtakes or paired transect data, and as a whole on Lake Erie, we performed 51 total overtakes. an example of what that data looks like. So this is transect 3 from this night, and you can see the paired data shows similar distributions and densities of fish from that 2-kilometer segment. So what we did from here was calculate aerial fish density from each of these paired transects, and then we compared them across the entire survey. So what are we looking for in this data? So here I just have some simulated data to give you an idea of what potentially could come out of this type of survey. So on the left here, we've got each of these dots are a pair of transects here. We could have an ideal scenario where all of the data are perfectly correlated and there's no bias, so there's no shift in the point clouds there. Another scenario is there's some bias or a shift in the point clouds, but we still have very good correlation between the points. Or more realistically, we may have some bias or shifts in the point clouds and a reduction in correlation. Another way to look at the same data is to use a bivariate plot where we put the RV or the research vessel and the USV on 2 different axes. Ideally, every point would fall along this 1-to-1 line, or we could have some potential bias where those points are shifted off the line, or again, more realistically, we have some sort of mixture of bias and correlation. So what did our data look like? It was a mix of both, but generally it looked pretty good. So on the left here, we can see that the USV and the RV data are covering basically the same span or range of density estimates. There is some crisscrossing of lines, so we don't have perfect correlation. There are a few that are really not good, but there are most of them are fairly good. When we look over here at the bivariate plot, there is some scattering, but all of these points fall along the 1-to-1 line, which is promising. But again, we collected this data with multiple vessels, multiple locations over a range of time, 2 months. So if we do kind of dig into the data, we could start to see some potential groupings that might need further explanation. So to account for this type of complexity in the data, we grouped the individual overtakes into 5 separate groups, and those are based on which vessel they were collected with, the Alomar, Muskie, Grandin, or Erie, Erie Explorer, the location, whether it was in the West Basin, Western Central, East Central, or Eastern Basin, and also the timing. So were those conducted in August or later September? We then fed the individual data in the groups into a statistical model. This is a hierarchical bivariate normal model. And this basically lets us estimate correlation and magnitudes of difference within each of these groups, but also collectively at the survey level. So what do we find from this analysis? If we look here at the left plot, again, we can see all of our individual data points in gray here, and the points are associated with those groupings. All of those points, as we saw before, fall along the 1-to-1 line. Importantly, though, the confidence ellipses also trend in the same direction of the 1-to-1 line. So the correlation in these groups is strong, and it's in a positive direction. The means of those groups, so these are the black points here, also fall along the 1-to-1 line. So here we have strong correlation both within and between groups. On the right side, we've calculated the proportional difference in the magnitude of the fish density estimates. So what we're looking for here is whether or not these points fall along this one line, so they're one proportional or 100% of each other. What we did see was that there were some differences within groups. So two of the groups, we actually saw higher estimates from the research vessels, and two of the groups actually saw lower density estimates from the research vessels. But when we look at these collectively, the difference at the survey scale is really minimal. There's only about 6% lower density estimates from the research vessels. So very similar at the survey scale, but we did have some context-specific differences within groups. So I want to touch on those context-specific differences and explain how those can be accounted for in future surveys. One of the issues that we ran into were rough survey conditions, which is a concern for any hydroacoustic survey. On the left here, I have a plot that shows vessel movement. The gray lines are the pitch angles of the sail drone, and the black lines here are the pitch angles of one of the vessels, the RV Muskie. And we can see that in these three situations where we had high wind and wave action, there was substantial movement of both of the vessels, but it was much lower with the research vessels compared to the USV. This is important because the movement of a vessel between pings can affect the accuracy of your data and may require correction. So that is something to take into consideration moving forward. Another issue with rough survey conditions is the data quality. So here I have two echograms from the same transect, one from the USV, one from the RV. In this situation, we had a lot of bubble interference. So bubbles that are produced at the surface can be washed below the vessel and degrade the quality of the data that you're collecting. The USV did pretty well, but the RV in this situation, we had to remove 24% of the data before we could calculate a density estimate from that. That's common or more common with large vessels that can really push a lot of bubbles beneath the hull of the vessel. Luckily, both of these situations can be avoided if you have flexibility in when you can collect that data. So sampling under optimal conditions basically eliminates this. And if we do have a USV on the lake for an extended period of time, we have more options for when we can collect data and use that data. Another issue that we all run into is spatiotemporal variation in the fish distributions. So we did run into this a little bit with our overtake surveys. When you're sampling at small 2-kilometer transects, you really need those transects to line up really well. And because the sail drone had to tack occasionally to stay on course, our transects didn't always line up perfectly. So in this case, you're actually potentially sampling slightly different fish distributions. We know that we can account for this by collecting larger volumes of data and essentially average out that small spatial variability. This is just some data illustrating this from the Lake Erie's eastern basin, where as we increase the number of kilometers that we sample, we reduce our relative standard error in the density estimate. So again, we know that with greater effort, we can reduce sampling error and improve precision of our estimates. Okay, so incorporating a USV into a survey. How can this benefit our understanding of prey fish abundances? So this is a snapshot of the Lake Erie survey from just this past year. We used 3 research vessels and were able to collect 450 kilometers of transect across the lake. This is pretty good coverage, but we do have some gaps. And in some parts of the lake. We used 2 research vessels to collect around 60 midwater trawls, but we're only able to collect those in the central basin. So, from a survey perspective, we're pretty much maxed out on the effort that we can apply to hydroacoustics and trawling. Now, based on what we found and generally what we know about sampling, we believe that we could improve the quality and the precision of our acoustic density estimates with using just a single USV. Based on the amount of ground we covered in our previous survey, we likely could cover potentially up to 1,500 kilometers of transects, which would substantially reduce our residual standard errors in our density estimates. But I think the biggest benefit here would be releasing our research vessels from acoustic data collection and transferring them to midwater trawls. So if we could retask those 3 acoustic vessels to midwater trawling, we could substantially increase the coverage and number of trawls that we collected, which would improve our understanding of species composition, prey fish species composition, expand our coverage, and enable us to generate whole lake species-specific density estimates. So that's what we think we can do. And why is this important, or why would this benefit management? Well, we know that prey fish, particularly pelagic prey fish, are likely one of the undersampled groups of fishes, particularly in Lake Erie. These fit, in the middle of the trophic ladder here. And we believe with better information on that, spatial and temporal information on species-specific abundance, we could really fill in the gaps with our understanding between the lower and upper trophic levels, and help inform what's driving production in Lake Erie, whether it's a bottom-up or top-down driven process. And ultimately, with this kind of information over time, we feel that could provide more context for management decisions that are occurring at the lower and upper trophic levels, whether that includes nutrient management or harvest assessments. So that's what I have for today. So I'd be happy to take any questions.